Hello, welcome to our textbook, Algebraic Structures with Applications. Now, the first comment I'd like to make is, what is an algebraic structure? Actually, that means different things to different people. If you talk to an algebraist or mathematician, when they think of algebraic structures, they think of some very abstract concepts called groups or rings or fields. There are other algebraic structures as well. These are three examples. And these are defined by axioms. And these are abstract systems, very abstract systems, and there are many, many examples in mathematics of groups, many examples of rings, many examples of fields. Now, in this class, we're going to focus on just groups. And there are many, many examples of groups that you're already familiar with. For instance, the complex numbers, modular arithmetic. Actually, matrices form a group. Okay, and there are many, many other examples as well. So the algebraic structures that we're going to talk about in this book are structures that are, in general, groups. And we're going to be taking a different approach from most algebra books. Instead of talking about groups in general and then looking at different examples of those general properties, we're going to be looking at these specific examples, making sure that you really understand them, and then seeing if we can understand some general properties from them, and in this way get some idea about what groups are. We're not going to talk in this course about rings or fields, although these are very important. I want to focus on groups because there are applications and there are many of these examples that you need to know that are groups, and it's good to see how they relate to this abstract notion of group. Okay, well, let's move on. All right, now this course is called Algebra. You've had classes with algebra before. You haven't had abstract algebra. So there is some relation, some similarity, and some with the courses that you've had in algebra, and also some difference. We're going to build on the things you know from algebra, but we're going to do things in a very different way, as you'll see. We're especially going to build on properties of these three number systems: integers, rational numbers, and real numbers. So we'll be using properties of these, and you will be doing proofs. Now, if you want to do proofs in a very formal way, we would have to go through and prove the properties of these number systems. However, this wouldn't leave us with enough time in the class to do what we'd like to do. So we're going to take kind of an informal approach and assume the properties of these number systems in the proofs that we do. So kind of want to get you some idea of what you can assume in your proofs. Basically, what you can assume in your proofs are the facts that you've learned about these three number systems in your high school and college algebra class. Now, here are some familiar properties of these familiar number systems: commutative, associative, distributive. I believe you've seen these in your secondary math class. These have to do with the operations, the order in which you do the operations. And here's a verbal description. And you should be able to write down examples of these three properties. For instance, associative, one example of the associative property for multiplication, say, would be 3 times 5 times 7 is equal to 3 times 5 times 7. All right, now, you're changing the order in which you're doing the multiplication. In this case, you do the 3 times 5 first and then the 7. And here you multiply the 5 times 7 first. Well, actually, and then you take 3 times that. Now, notice that we are preserving the order. We still always have 3, 5, and 7 in this order in both of these two expressions. If you change the order, that's what's called commutative. Okay, and there's distributive involves both multiplication and addition. So you can refresh yourself on these properties. So you're allowed to use these properties of the integers, real numbers, rational numbers without proof when you do proofs in this class. Okay, so it's a good exercise to make sure that you can do a statement that illustrates each one of these statements here. Now, these statements can be used in proofs. So let's look at a simple example. All right, and these statements, by the way, these statements don't work for all operations. For instance, subtraction is not commutative. You should be able to give some example. If you remember commutative for addition is 3 plus 5 is equal to 5 plus 3. That's commutative for addition. And you can see if you can think of an example in subtraction which shows that subtraction is not commutative. Okay, now let's look at this exercise here. Suppose A is greater than B, B is greater than or equal to 0, and AB is equal to 0. What can you conclude about B? Use one or more of the properties we've mentioned to justify your answer. So this is kind of the way you're going to be doing proofs, is you have a statement that you want to show something about, and you have certain properties or statements that you know are true, and you want to use those in order to make a statement about this. So we hope we can use these properties to say something about this. Now, you need to be very careful when you do this exercise to make sure that all of your conclusions are justified. And again, in this case, you want to use properties that you know of that have to do with, here we're talking about real numbers A and B. So we use these types of properties to prove things about, say, real numbers or integers or so on. Let's look, for example, at exercise 3 down here. All right, so take a look at this. It says, suppose A is greater than B, B is greater than or equal to 0, and AB equals 0. Now, it doesn't say what type of numbers these are. Typically, when we just talk about numbers, we assume that they're real numbers. So what can you conclude about B? Use one or more of the properties we've mentioned to justify your answer. Okay, so typically when you have to prove something, you go back to properties that you've shown and see if you can use that to conclude something here. Now here we have a product of AB equal to 0. So if you look back at this list of properties, this seems to be a relevant statement. If the product of two numbers is 0, then one or the other number must be 0. Okay. Now, here we have AB equal to 0. So by that last property, so if I was going to answer this, I would say by the last property. I'm going to abbreviate to save time. One or the other of A and B has to be 0. Okay. Now, we haven't finished the problem because it says, what can you conclude about B? So far, we haven't concluded anything about B. We've only concluded that either A equals 0 or B equals 0. We would like to conclude that B equals 0, but we're not there yet. In fact, to conclude B equals 0, we're going to have to use another property to show that A is not 0. And I'll leave that to you. Just take a look at these conditions here and see if you can do something with these conditions and the statements above to show see if you can show something about B. So that's all I'm going to say about this exercise. Well, let's move down. Now, one thing you've done in ordinary algebra is manipulate equations, and we'll be doing more of that in abstract algebra as well. Basically, you can do the same thing to both sides of an equation. You could subtract you can do substitution in an equation. You can multiply, divide an equation by the same thing. You can reduce fractions to lowest term. These are all operations that you're familiar with. This exercise gives you a chance to refresh yourself on what these mean. Another important operation that you learned in algebra is exponentiation. And you really do need to know your exponent rules. And here they're listed verbally. You can, again, have an example to write equations to remind yourself what these are. So here are some exponent rules that you can test yourself on. And there are several examples here, so you really should test yourself on this. Make sure that you don't get slipped up. Here's a chance to solve for all solutions to the following equations. Now, you know an equation can have more than one solution, so be careful. You get all possible solutions that you can find. All right, well, that's pretty much it for the introductory chapter.